Dear friends, in this episode and the following ones, we shall be discussing the dynamic processes that act on the earth in the regional scale. As you all know that our planet earth is a very dynamic planet. A lot of movement goes on the surface of it and below the surface deep into the mantle. You have already been told about the shell like structure of the earth, of which the uppermost rigid layer is known as the lithosphere. The movement of the lithosphere, or more specifically the crustal uppermost layer, has resulted in the formation of long mountain chains, because the mountain chains like the Alps or the Appalachians in Europe and North America have been studied by the European and American scientists for a long period of time, and when Asia was under British rule, the Himalayas were also subjected to analysis and investigation by scientists. The Alps and the Himalayas as well as the Appalachian mountain chains were found to be products of large scale earth movements, in which the horizontal compression caused pre-existing sedimentary layers to become folded and develop into long chains of mountains, with the core occupied by plutonic igneous intrusions. These mountain chains were called orogens, and the process of their formation were called orogeny, development of mountain chains by horizontal earth movements. We shall be discussing about the movements of the lithosphere in some detail in the following episodes. Apart from the horizontal compressional movements that cause the upliftment of rocks into mountain chains, there are certain vertical movements of the asthenosphere that is caused by either isostatic adjustment or movement along brittle fractures or normal and thrust faults. Such vertical movements of the earth's crust resulting in the upliftment, elevation of certain areas are known as epirogeny. The surface of the earth was not static but dynamic, has been established long ago when sailors moving around the high seas around the world in the 16th and 17th centuries completed drawing the maps of the world's continents. It was observed that there was a jigsaw puzzle like fit across the Atlantic Ocean. The bulge on the eastern coast of South America and the notch on the western coast of Africa appeared to be fitting into one another, as if they were once together and have been brought away from each other by some divine hands. However, subsequent observations proved this, that they were really together at some time. These observations that similar topographic fit, similar fossils, similar rock types are found across the ocean basins led some scientists to believe into establishing a huge supercontinent, which later broke up and drifted apart. In 1912, Alfred Wegener, an Australian meteorologist, proposed the theory of continental drift. He said, with the evidences of identical fossils across the Atlantic Ocean in South America and Africa, with the occurrence of similar rock units in these two continents, with the continuation of structural trends and rock types in the eastern part of North America and the western part of Europe, he suggested that the continents were once joined together into a single supercontinent and then drifted apart or moved apart from one another by some physical processes. Though his evidences were really sound, that indicated that these continental land masses were once together, but the difficulty in establishing his theory was the problem that the continents, which were by then known to be made up of lighter granitic material, how they could move through the denser oceanic material which is made up of basalt. He could not offer any explanation or physical process or dynamics of the movement of continents ploughing through the dense basaltic crust. While Alfred Wegener was unable to substantiate his theory of continental drift because the dynamics was unavailable, a parallel theory of evolution of the earth's surface was in vogue. This theory, known as the geosynclinal theory, was believed by most of the tectonic scientists, who considered that initially there were some linear depression called geosynclines, in which the sediments were deposited and they bent downwards and were pushed up to form mountain chains or orogens by horizontal earth movements. However, this theory is now neglected because it has been proved that no orogen always follows the evolution as a geosyncline. But we must remember at this stage that some of the terms associated with the geosynclinal theory are still in use, though slightly modified. Especially during the Second World War, some observations were made on the ocean floor. These observations were made by the submarines that were travelling close to the ocean's bottom for finding routes for the Allied forces across the Atlantic Ocean, because the surface was ruled by the German Navy. While trying to find out the routes, the scientific measurements made on board the submarines indicated that across the mid-oceanic ridges, the long line of mountain chains occurring on the ocean floor, there are symmetrically disposed stripes on which the magnetism or magnetic intensity was alternately reversed. There was positive magnetic anomalies or an ambient magnetic field that was higher than the Earth's magnetic field, alternating with stripe of negative anomaly, a zone where the total magnetic intensity was lower than the ambient magnetic field of the Earth. These alternating stripes of magnetic anomalies was puzzling to the scientists, but some of the scientists later came up with the theory that this might be produced if there was origin of the oceanic crust at the mid-oceanic ridges. When this oceanic crust cooled, the magnetic minerals were magnetized with respect to the ambient magnetic orientation of the Earth's polarity, and then they split into two and moved apart away from the ridge crest. A new oceanic crust formed, and this new oceanic crust was magnetized by the Earth's magnetic field, which was reversed. This process continued for a large length of time until the oceanic crust gradually moved towards the boundaries of the oceans and disappeared. The observation of magnetic anomaly stripes, alternating negative and positive magnetic anomaly stripes symmetrically disposed against the axis of mid-oceanic ridges, led several scientists to establish the seafloor spreading hypothesis. Among them there was Hess, there was Vine, there was Matthews, which can be read in any textbooks. The seafloor spreading hypothesis solved two problems. It solved the problem of the physical observation of alternating symmetrically disposed magnetic anomaly stripes, and it also solved the spreading apart of the supercontinents. They proposed that the continents did not move apart on their own. The continents were part of the oceanic crust. When the new oceanic crust formed and moved apart, they carried the continents on it on their back. Thus, the problem of Wegener's dynamic problems, that how continents can move through denser oceanic crust, was solved. The seafloor spreading hypothesis was a giant step towards explaining the evolution of the surface features, the large scale tectonic features of the earth. Since the early 1960s, several scientists across the earth were interested to explain the earth movements. Though seafloor spreading was a great help, it was not able to explain all the features that develop on the earth's surface. Gradually, the conception of plate tectonics came into existence. The plate tectonics believes that not only the crust, not continental crust, not the oceanic crust, but a part of the upper mantle, which is the next lower shell, forms a rigid outer layer of the earth. This rigid outer layer, which they called the lithosphere, nearly floats over the lower level of the mantle, which they called the asthenosphere. According to them, the lithosphere in the present day earth is split up into a number of fragments, many large and many small. Due to the fluid nature of the asthenosphere, which allows the lithospheric fragments to move over them, the dynamic processes active into the mantle causes the lithospheric plate fragments to move apart from one another. This is broadly the basic principle of plate tectonic hypothesis or plate tectonic theory. The plate tectonic theory solved many problems. It was able to solve almost all the tectonic structures. It was able to explain all the possible structures that are found on the earth's surface. The advantage of plate tectonic theory is that it can be explained easily with the known physics and dynamic processes that act in the inside the earth or at the surface of the earth. Thus, there was a paradigm change in the conception of tectonism, and the plate tectonic theory is now believed to be the solution to all possible questions. However, there are certain situations which cannot still be explained by the plate tectonics theory. The plate tectonic theory believes that the lithosphere behaves as a rigid material floating over the asthenosphere, which is a viscous layer. Rigid material means that no deformation that takes place at the boundaries of the plate fragments are transmitted inside the plate fragments, so that all the deformation that are expected will be confined to the boundary regions or marginal regions. However, it is observed that several deformation, diastrophism or tectonic disturbances do take part inside a plate. Thus, they cannot be taken as completely rigid. Except these small hitches, the plate tectonic theory is able to explain almost all the features that are observed on the earth's surface. The plate tectonic theory proposes that the plates move apart against certain regions, which are represented by the mid-oceanic ridges on the ocean bottoms and certain rift regions on continents. The example of the first being the mid-oceanic ridge or mid-Atlantic ridge, the East Pacific rise, the Indian Ocean ridge, etc. While the example of the second continental boundaries from where the two plates move apart are the East African Rift Valley. Since the surface area of the earth should remain constant, if the plates move away from one another along divergent plate boundaries where new lithosphere is created, some of the old lithosphere must get destroyed at some boundaries. It was found that such a destruction do take place. They take place at boundaries around the Pacific Ocean, where the heavier, denser and older oceanic crust is going below the younger oceanic crust or young continental crust, so that the subducting plate gets melted at depth and the area of the earth remains constant. Most of the divergent and convergent boundaries are found to be running north south or slightly at an angle to it, but where do they stop? They do not run continuously across the earth. Tuzo-Wilson suggested the type of a fault against which the two plates move side by side. Thus, three types of plate boundaries are identified: the divergent or constructive plate boundaries, where new lithosphere is created and moves away from one another; convergent plate boundary, where the two plates come together and also are destroyed; and the transform boundary or conservative plate boundary, where lithosphere is neither created nor destroyed, they simply move in a horizontal direction along the plate boundary. At divergent boundaries on the ocean floor, where new lithosphere is created, its thickness is almost nil and it is very hot. As the new lithosphere moves away from the mid-oceanic ridge, it becomes cooler, denser and thicker. Due to the elevation of the ridge crest on the ocean floor, there is a gentle slope of about 5 to 10 degrees away on the sides. On these slopes, some of the important or interesting metallic deposits are found. We will be discussing about these deposits in our next lecture. At convergent plate boundaries, there are three categories. We will be discussing them in detail. At convergent plate boundaries, two oceanic plates may come together, one oceanic and one continental plate may come together, or two continental plates may converge together. The example of ocean-ocean convergence can be found on the western coast of the Pacific Ocean, where the Pacific plate is subducting below the Philippines plate or the Asian plate, extension of the Asian plate. About the ocean continent convergence, example can be found on the eastern coast of the Pacific Ocean, where the Nazca plate forming the eastern Pacific Ocean floor is subducted below the South American continental plate along the Peru-Chile trench, and two continental plates converging together may be observed at the Indian Asian collisional zone, where the Indian continental landmass and the Eurasian continental landmass have collided together and thrown up the intervening sediments to form the Himalayan mountain chain. Transform or conservative plate boundaries show a kind of strike slip movement of the divergent plate boundaries or convergent plate boundaries that they join. They are mostly found across the divergent plate boundaries or mid-oceanic ridges on the ocean floors. However, some of the continuation of the transform plate boundaries may be observed on continents. For example, the San Andreas fault on the western coast of North America. The surface features of the earth, like the long chains of mountains that show intricate fold and thrust structures in them, the occurrence of zones of seismic activity, the occurrence of oceanic fracture zones running across the mid-oceanic ridges can all be explained by the plate tectonic theory. Along the Himalayan or alpine mountain chains, it has been observed that a movement of a horizontal movement of the lithosphere in a north-south direction has resulted in the formation of east-west trending large scale folds and east-west striking thrusts, together with steep dipping normal faults or strike faults that can be explained in terms of the movement of the lithosphere. It has long been observed, especially along the coast of Japan, that a zone of deep seated earthquake foci occur parallel to the Japanese islands. These identification of this zone was made by Benioff and Wadati, two physicists, and have been named according to their name as Benioff-Wadati zone. The explanation for this zone can easily be obtained from the theory of plate tectonics. It has been found that the Pacific plate subducting below the eastern extension of the Asian plate around or below Japan goes up to a certain depth, which is about 670 kilometers, and this is the lower limit of the seismic foci that are generally measured. The distribution of earthquake foci along this zone also coincides with the downgoing Pacific plate. Thus, it was explained that the frictional forces resulting in the downgoing or subducting plate caused by the resistance of the mantle causes some strain in the subducting layer. The inclined Benioff-Wadati zone below Japan can be easily explained by the subducting Pacific plate, because it has been observed that the zone of seismic foci coincides perfectly with the downgoing Pacific plate up to a depth of 670 kilometers nearly. It has been explained that the rigid lithospheric plate going down into the mantle faces some resistance from the mantle, and this resistant force causes the development of strain within the downgoing plate. When the strain exceeds the strength of the layer, there is brittle fracturing or faulting, and the earthquake waves are generated from these faults. The oceanic fracture zones that run across and are observed to displace the mid-oceanic ridge crest are also explained by the plate tectonic theory, because the oceanic fracture zones are believed to be continuation of the transform fault boundaries that causes displacement of the mid-oceanic ridge crest. Around the mid-oceanic ridge crests, there are sometimes displacement of the magnetic anomaly stripes, which cannot be explained by any brittle fracturing. This has been explained by the progressive development of one of the segments of the mid-oceanic ridge at the expense of the other, so that if their orientations are different, the magnetic anomaly stripes will also have a different orientation, thus causing an appearance of displacement or pseudo faults. It has been observed by geologists across the continents that fossils, especially land fossils of similar age like the Gondwana flora of Carboniferous and Permian age, are distributed all over the southern continents like South America, Africa, India and Australia. Since they were land plants and could not have travelled across the seas on their own, these continents must have been together during that time. There have been observations of coral reefs at much higher latitudes. We all know that coral reefs occur only within a very small zone of latitude around the equator. The occurrence of identical basaltic lavas across the Atlantic, the occurrence of continental basalt flows across the Atlantic of identical chemistry and origin, these all indicate that these continents, which are now separated by the large oceans, must have been together at some point of time. However, as we have discussed, the theory of continental drift as proposed by Alfred Wegener was unable to explain how the continents move apart, what causes their movement apart by moving only the continents and not the oceanic crust. This was solved by the next theory that evolved through observations made especially during the Second World War. At the end of the first episode on the physics and dynamics of the earth, Let us briefly recapitulate what we have learned. We have learned that our planet is a dynamic planet with movements going on both at its surface and deep below. The internal movement dynamic processes causes the movement of the surface. The surface is made up of a number of fragments of a hard rigid material called the lithosphere, which is made up of the crust and the uppermost part of the mantle. These plates or plate fragments, they move past one another and have three types of plate boundaries separating them: divergent plate boundaries, from which the plates on either side move away from each other; convergent plate margins, where two neighboring plates come together and one either goes down or the two collide to form mountain chains; and 3, transform plate margin or conservative plate margin, along which the two plates move past one another without forming a new lithosphere or destroying the old one. Thank you.